Have you ever watched a football spiraling perfectly through the air and wondered how it stays so stable? But then you see a plate wobble in the air and it just seems to go completely wild. Well, let's get into it because the physics of spin is honestly one of the most fascinating and surprisingly complex parts of our world.
And you know what? It's not just us who find this stuff weird. We're talking about two of the absolute giants of quantum mechanics, Wolfgang Pauli and Niels Bohr, and even they were totally captivated by the simple motion of a spinning top. It's one of those things that looks simple on the surface, but it's like a doorway to some really deep physical truths.
And it wasn't just old-school physicists and tops. Picture this, the legendary Richard Feynman, just sitting in a cafeteria, sees a guy toss a plate. He noticed this weird little detail. The plate's medallion was spinning faster than the plate was wobbling, and that tiny nagging observation actually set him on a path that helped him win a Nobel Prize. Isn't that wild?
So what is the deal with spinning things? From a kid's toy to a dinner plate, all the way up to the wobble of the Earth itself. What are the hidden rules behind all this weird and wonderful motion? Well, today we're going to unpack them.
Okay, so to really get this, we've got to build ourselves a little physics toolkit. And the very first tool we need is just a way to talk about spin itself.
First up, angular velocity. Yeah, physicists use that Greek letter omega for it, but don't get hung up on that. The best way to think of it is as the rotational cousin of regular speed. But here's the key. It doesn't just tell us how fast something's spinning, it also tells us the direction of its spin. Simple enough, right? All right, so we've got speed. But that's not the whole picture, not by a long shot. The next piece of the puzzle, and this is where it starts to get really cool, is all about the object's shape. This brings us to a concept with a kind of clunky name, but it's super important, the moment of inertia. The easiest way to think about it, it's rotational stubbornness. Seriously, it's just a measure of how much an object fights you when you try to get it to spin or to stop spinning.
And the comparison to regular motion is just perfect. We all know it's harder to push a heavy bowling ball than a light tennis ball, right? That's its mass. Well, moment of inertia is the exact same idea, but for twisting and spinning motion.
But here's the twist, pun intended. It's not just about how heavy something is. It's all about where that weight is. For example, a solid disk is much easier to spin than a hollow ring of the exact same weight. Why? Because all the ring's mass is distributed way out on the edge. When it comes to spin, how you spread the weight out is everything. That's the key.
Okay, we've got our first two tools. Now for the last one. This is the big one, the concept that ties it all together and finally explains why some spinning things are so stable. And that concept is angular momentum. It's basically what you get when you multiply the rotational stubbornness, that moment of inertia, by the spin speed, or angular velocity. But here is the secret sauce. This is one of the most fundamental rules of the universe. In any isolated system, angular momentum is always conserved. It does not want to change, period. You've all seen this. Think of an ice skater. They start a spin with their arms stretched way out, right? Then they pull them in tight to their body. And what happens? They spin crazy fast. They haven't changed their weight, but by pulling their arms in, they've massively decreased their moment of inertia. And since the universe demands that angular momentum stays the same, their spin speed has no choice but to skyrocket to make up the difference. It's pure physics, right there on the ice.
Okay, toolkit complete. We've got spin speed, rotational stubbornness, and this conserved quantity of motion. Now, let's go back to that cafeteria and solve the mystery of Feynman's wobbling plate. Seriously, you can try this right now. Grab your phone or a book. If you flip it along its longest axis, see? Nice and stable. Now flip it along its shortest axis, like end over end. Also stable. But now, try to flip it along that weird in-between intermediate axis. It just goes crazy, right? It tumbles all over the place.
And that's it. That's the secret. It turns out objects only like to spin in a stable way around their longest and shortest axes, the ones with the biggest and smallest moments of inertia. That middle axis, it's just naturally, fundamentally unstable. And Feynman's plate, it was just a victim of being spun around that wobbly middle axis. Boom, case closed.
But okay, this isn't just about books and plates. Let's scale this idea up. Way up. I'm talking planetary. Our Earth, you see, isn't a perfect sphere. It bulges a little at the equator, kind of like it's been squished slightly. And that, in physics terms, makes it a gigantic spinning top.
And way back in the 18th century, the brilliant mathematician Leonhard Euler used these exact same principles. He sat down, did the math, and predicted that because of this squished shape, the Earth's axis of rotation should wobble slightly, completing a full circle every 300 days.
But then came another puzzle. When astronomers in 1891 finally managed to actually measure this wobble, which we now call the Chandler wobble, they got a different number. It took 435 days, not 300.
So what's going on? Why the huge difference of 135 days? Did Euler, one of the greatest mathematical minds in all of history, just get it wrong?
Well, no. Turns out his math was perfect. His assumption was just a little too simple. He treated the Earth like a perfectly solid, rigid rock. But it's not. Our planet is kind of squishy. It has sloshing oceans and a dynamic atmosphere, and all that flexibility acts like a drag, slowing the wobble down from his predicted 300 days to the 435 days we actually see.
Okay, so we've gone from spinning toys to cafeteria plates all the way to our entire planet. It's a really cool puzzle for sure. But so what? Why does any of this actually matter in the real world? Well, take a look at this. This is the asteroid Toutatis. Notice anything? It's not spinning nicely. It's tumbling chaotically all over the place. It's basically a giant cosmic tennis racket flipping on its unstable axis. And if you want to predict where a giant rock like that is headed, you'd better understand this physics.
And this stuff is everywhere. This is the physics that lets us keep our satellites pointed in the right direction. It's what goes into designing agile robots. It's absolutely crucial for tracking asteroids that might get a little too close for comfort. And yeah, as Feynman proved, these ideas can even spark breakthroughs in the bizarre world of quantum mechanics.
But I want to leave you with one last thing, a real unsolved mystery. Remember that squishiness of the Earth that slows the wobble down? Well, that drag should have caused the Chandler wobble to die out completely ages ago. But it's still here. Something is constantly giving it a little push to keep it going. Maybe it's pressure shifts deep in the ocean, or maybe it's the effect of earthquakes. The honest truth? Nobody knows for sure. So what do you think is keeping our planet wobbling?